Let's begin. This is a 3-session lecture condensed into one. So I'm going to zip through the whole thing. What I aim to do, right, is not to give you a thorough kind of explanation to everything gravitation. Rather, right, I want to give you an appreciation of field. Okay, this idea called field through the context of gravitation, which you have learned before. Okay, and then right, to help you appreciate E field, which you are going to learn either in the next topic or the next topic for most schools. Yeah, that's always the second or third topic in most schools. So that is the intent. So if you find that I'm going too fast at a certain point and you are not following, right, don't worry. Go back and look at the notes again. There are lecture examples. Go and try them and you'll be fine. Okay. So I make my intent clear. So today, right, we really want to appreciate how field work through the context of, through the lens of gravity. So let's first understand how gravity works. Gravity, right, as with all fields, okay, always have a property, right, that is related to the field itself. So for gravity, right, the field is related to mass. So suppose, right, you have the people featured in this slide, right, will hate me, okay, because they hated me once already when I used them in my lecture. So now I'm going to use them in this session. Yeah, so these are my ex-students, okay. These are not how they really look like, okay, but they used to be a bit on the plump side. That's why I use them, okay, but they are now very fit, okay, and very lean. So gravitation is attractive in nature. You see the and how large is the force that they attract each other with? Well, it's just given by this formula, and this formula, right, is talking about, right, the force is proportional to product of the masses. That's the first thing. Next thing, right, is inversely proportional to the square of separation. And since, right, we are talking about a proportion relation, as with all proportion relation, right, you have a proportional constant. So that constant is this capital G. Every time, right, people look at this formula, right, especially those who are very new, right, you look at this formula, you feel very intimidated. Why got this thing G? But it's not to be unexpected because, right, in physics, we deal with a lot of proportion relation. It's just, right, in the past, there are some situation whereby the proportionality constant happens to be 0. For example, F equals to dp dt. Net force is proportional to rate of change of linear momentum. You see, why don't have a constant? The constant is there. It's just 1. Here, the constant is G. This G is very small. You see the absolute number, right? Is 6.67 times 10 to the power minus 11. It tells us that by nature, gravity, right, is weak, okay, compared to other things, compared to other things. So when you want to compare to another field, right, you just look at their constant. It'll tell you, right, a relative sense of strength. Yeah. So if you have only 1 kg or M1, 1 kg, M2, and they are 1 meter apart, then this field is very, very weak. Okay. If M1 is 1, M2 is 1, R is also 1, right? Then the force is 10 to the power minus 11 Newton. So that tells you how weak this is. That's why, right, you can only feel gravity, right, when you're talking about gravity due to a planet, when the mass is like 10 to the power 20 something, 30 something. Yeah. This is the same relationship in words. This is what you write in exam, no exception. The only thing I want to bring your attention to, right, is let me go back. Why do we say particle here? Okay, why do we not just say every mass attract every other mass? There's a meaning to why we say particle. It's because particle, right, is like a point. There is no dimension to it. Yeah. And if there is no dimension to it, right, then it's very easy to define the separation between them because you're just drawing the line connecting one point to another point. Okay. If you're talking about real mass, right, with a size, and the mass don't even need to be spherical, it can be a square, any shape. Then, right, where do you define the separation? Yeah. So that will be more difficult. But of course, we can also say that, oh, then it's from center of mass to center of mass. Yes, that is possible. Okay. So if you are creative and you just want to say things in your own way, then you have to be very sure that whatever you say is conceptually accurate. This definition is perfect. No problem with it. So if you just write this, right, you can just say that it's square of separation between them, because then where are they? They are the point. And that is very precise. No ambiguity. Okay. Now, right, let's appreciate this thing called inverse square law. Inverse square law is very common in physics. And you may wonder, right, why got this kind of inverse square relationship? Well, the last time you see inverse square, right, is probably in a chapter of waves, when you're talking about intensity, right, of the certain wave source at a certain distance r away from the source itself. And the source is an omnidirectional source. So you will have the power, intensity equals to power over 4 pi r squared, something like that. So similarly, right, in gravity, right, because who is creating the effect? It's a mass. It's a mass, right, at a point. And this effect, right, is felt uniformly throughout the three-dimensional space, or it emanates outwards from a point. Therefore, right, if you want to find like how strong is the effect, right, at a certain point, then you have to ask, right, how much have this effect spread out? So the spreading of this effect, right, will lead to a 1 over r square relationship. Okay. Do you follow this part so far? So with that, right, we can just appreciate what does that mean. Simply, right, you can just put in a number. If you, right, double their separation, you expect, right, the force to be 1/4. So this is simple terms, right, how you say inverse square law. Or double separation, get 1/4 the output. Yeah. And just now we mentioned, right, we are talking really about particles, and we like to use particles, okay, for the fact that, right, it's unambiguous when you want to define where they are. Yeah. So for this Fuxin and Ziyu, right, we want to simplify and understand them, right, as though they are particles or string into a certain point. Okay? But if they are not, right, then no worries. We'll just consider center of mass to center of mass. Okay. Now, right, next question to ask, right, is suppose, right, one of the object is larger than the other one. What will happen to the force they exert on each other? Originally, it could be both are the same, but now, right, consider if one is larger, what may happen to the force? Often, right, people have a misconception. They think that, right, the bigger guy attract the smaller guy with a bigger force. The smaller guy attract the bigger guy with a smaller force. You may think that, oh, I don't have these misconceptions. But right, these misconceptions, when phrased this way, right, it's like very clear cut. I mean, everyone understood it, okay? But there will be some situations, right, that you actually will, your instincts will come out and guide you and lead you to the wrong conclusion, which is big guy will exert a big force, small guy exert a small force. Not correct, okay? When they are attracting each other, right, you should always understand this from a Newton third law point of view, that the force is always the same one. Yeah. And if you look at the formula, right, whether is it m1 times m2 or m2 times m1, they are the same thing. Yeah. So there's no sequence of attraction. No say big attract small is bigger, small attract big is smaller kind of thing. Okay. So the mass the force are the same. Now, right, let's understand this idea of gravitational field. Suppose we look at the Earth, right? We don't see this gravitational field, but we feel its effect all around. And we know, right, it's sort of a stronger, nearer to us, weaker, further away from us. Yeah, same for every planet. So whenever a mass is there, right, you'll set up a region of space, right, whereby you'll feel some other mass will feel gravitational force. That is, in essence, right, what is meant by G field. Or G field is a region of space where a mass experiences gravitational force. This will actually come out in exam 1. Or what is meant by a gravitational field? Or what is meant by a field? A field is a space or region of space where an object possessing a certain physical property that is acted upon by the field to experience a force. Okay. Or when we say G field, you can just say where a mass experiences a G force. But if you're talking about generic field, then you have to make the explanation generic. Yeah, and we can represent field, right, through this thing called field lines. Oh, this is important. In E field, in B field, super important. G field, we don't see much because, right, there are many other ways to represent G field, and usually we're not too particular about the representation of the G field lines, okay, the shape of the lines and so on. We have other ways to test you. But this concept, right, is actually applicable in across all fields. So we look at these lines, right? What do we notice? These lines, right, is always, right, emanating from a point, okay, and it's always pointing towards the center, okay. And which direction do the arrow point? You just have to ask, okay. If you put another mass at some other point, what is the direction of the force? That will tell you, right, the direction of the field. So for gravity, right, you put any mass nearby this M1, the force that you experience, right, will be always towards M1. Okay, so these lines, right, will always be pointing inwards. This definition that I just said, right, may feel, hey, so easy, or isn't it obvious? That is obvious, right, because we are looking at gravitation, because it is a purely attractive force. In electric field, there will be attraction between positive and negative charged particle. There will be repulsion between positive and positive, negative and negative. In such a context, right, the field come in very crucial really, because there is a protocol one to define what is the direction of the field. Yeah, so don't ignore things, right, simply because they look obvious in gravity, because you will fail to understand, right, the even more basic structure, right, that other topics definitions are built upon. Let's define what is a gravitational field strength. Okay, it is the gravitational force per unit mass. This is very important. Once you understand this line, right, it's actually saying it has part. First part is saying it's a gravitational force. Second part is saying, right, per unit mass. It's just like going to the market, right, and saying, right, what is the price of the salmon? Okay, so price of the salmon, right, could be, say, $30. But $30 not very meaningful, right? Because, right, how big is your salmon? How big a piece do you buy? So if you want to understand, right, how pricey it is, you should ask, right, how much is the salmon per kg? Then people tell you, oh, it's $20 per kg. Yeah. And because, right, if you want to compare buying salmon versus buying cod, okay, you can't just say, oh, salmon costs $30, cod costs $20, and you just say, oh, salmon is more pricey than cod. Not true, because that piece of cod, right, could have been $50 per kg, or salmon is $20 per kg. So you see, when you want to compare field strength, which is, right, how strongly the field is, okay, you must compare it, right, by a per kg denomination, so that you are purely looking at the property of that point in a gravitational field, without thinking about, right, what do you put at that point, what mass do you put at that point for the gravitational field to exert upon. So you want to remove the consideration of what you put there. Just consider how strong is the property at that point. Yeah. So with that, right, that is the gist of this definition. Very important. And if you were to write a formula, right, for G, it'll be G is equals to F over M. Do I have it in my slides? I think I didn't have it here. So G is equals to F over M. That gives you, right, the definition in an equation form. So you shall not say, right, G is equals to Gm over R squared. That's incorrect. That is a G due to one mass. G at a point, right, is more generic. It's just F over G, because you don't know who is contributing the field at that point. It's just a point in the gravitational field. How you know what's how strong is the field? You put a mass there to test log. Then you take the mass divided by you take the force divided by the mass. That gives you the strength at that point. Oh yeah, I have a slide. I forgot. Because I forgot what will appear in the animation. So I thought, forget that all these things will show up. Okay, and suppose, right, you have two mass scenario like what we saw at the beginning, right? So you know that the force is simply Gmm over R squared. So if you want to consider, right, at point where M2 is currently at, what is the G at that point? So you simply take, right, the force experienced by M2 divided by M2 itself. So you see the Gmm over R squared, right? Okay, here, the M2 and M2 will cancel out, leaving only Gm1 over R squared. Okay, and this is how the Gm over R squared thingy equation come about. It's a special case, okay, arising from this four fundamental result, which is F over M. Okay, this is a special case for just one mass contributing the gravitational field. Just a quick note, two possible unit, Newton per kg or meter per second square. Okay. Suppose, right, we have the G field set up by M1. Okay, that is given by the blue lines. And we also have the M2 being placed there. Okay, and M2 experience this force. So you know that F is equals to M2 times G1, which is the G due to M1. Then, right, this allows us to take out the M2 and write G1 as the Gm1 over R squared. Okay, and once again, right, there is another way of looking at Y, right? That point, the force is equals to Gm1 M2 over R squared. Okay. Now, right, we can do the same thing. It's a bit repetitive. I'll skip. Okay. Now we look at the scenario, right, whereby we have multiple bodies. Suppose we have both M1 and M2. They each contribute a set of lines, right? These lines do not appear together, because, right, in a region of space, if there are two sets of gravitational field line, you won't see the two sets separately. At every point in space, right, you will always do a evaluation, really. Okay, so if there are two fields, then you have to evaluate what is the resultant. So what you have, right, is only one set of field, not two sets. Okay, and how do we actually go about doing that? Let's pretend, right, to place one particle there, or a third guy. We put a third guy there, right, and we ask ourselves, what will the force the third guy experience? So, right, you see, the force that the third guy will experience, right, due to M1 will be given by this arrow. Okay, the G at that point. And due to the second guy, or M2, you'll be like this. So if you want to find, right, what is the resultant, so you just take the vector sum of these two arrows. So that gives you resultant, and that's how you evaluate in problem solving. Okay. And yeah, what if you have another mass or somewhere there closer to M2? Then right, you expect that the resultant force will be like that. Okay, and this guy will experience a force that way. Yeah, you notice right, the path is not a straight line because as it moves right, it will land into a new point in a G field. The new point in the G field will have a different resultant G, and it will interact with the velocity right in a new way. Okay, you don't need to calculate. You just need to know right. It's not going to be linearly. Okay, going down according to the initial force direction. Now right, let's also appreciate the fact that right this G due to a single mass follows the inverse square law as well. So at twice the distance away, you have 1/4 the gravitational field strength. So let's look at the force right exerted on different masses. Okay, small object, small force; big object, bigger force. Okay, yeah, but yet right, the G also affects or also influence how large the force is. Yeah, so that's how mass and the field come in to the picture to decide how big the force is. Now right, if you were to remove the idea of field and force, and let's go back to looking at the Newton's second law, F equal to ma. So we notice right that at every point right, the force is equals to mg, and by Newton's second law, mg will be equals to ma. Yeah. So it turns out right that the g at any point will tell us what is the a. Yeah. Hope that this is not surprising. This should be a very straightforward thing. Oh, so the g simply tell us the a, which is why right the unit of g is also meter per second square. Yeah. It is both a force per unit mass, so Newton per meter, Newton per kg, but it is also meter per second square because the effect that it delivers is an acceleration. Okay. Now let's study the G field. What are the characteristics? Closer to the mass, right, we see that the G field lines are close, or one line to the next line is like really close. You go closer, even closer. So close lines with tell us that the field strength is large, or so large G, and vice versa. Far apart lines tell us it's a small G. Oh, this is not difficult, it's straightforward also. But right, this is important to know, right? Next time when you are doing E field or magnetic field, whereby you deal with field lines a lot, all these intuitions, right, must be automatic one. You must know this right quite well to appreciate the E field and the B field very fast. So it starts off easy, right, in the context of gravitational field, which is actually right the easiest field of all. Because gravitational field is very straightforward. It's purely attractive. Okay. E field is no longer straightforward because it could be have two different nature depending on the charges in question. Yeah. Now right, we are going to do this exercise right whereby we must visualize. I help you visualize through the slides, but you must visualize more and more later on. Which is right. What if we zoom in towards M? And let's see right how the field lines will look differently. So let's zoom in a bit. Okay. So now right, you zoom in further and you see that the orange line here is the surface of M. Okay. And now you see the lines right like appear further. That's because we are taking a different zoom scale. Yeah. But if you zoom in even further, right, you see the lines, it will appear like that. Yeah. And once you zoom until this level, right, you could see some pattern already. The lines, right, actually look quite parallel. The lines look quite parallel. Of course, right, we don't stop here. We're going to zoom in even further. So at such a zoom level, right, whereby you see the curvature of Earth disappear and all you see is a flat ground, what you notice, right, is that the gravitational field, number one, right, will be all parallel. Number two will be all equidistant. Okay, let that sink into your head. And I'm going to repeat, right, this point I just said just now. When the lines are far, it means that the field is weak. Lines are close, it means that the field is strong. If the lines are evenly spaced, what does it mean? If the lines are evenly spaced, what does it mean? What does it imply about the field? Anyone want to try? When the field lines are parallel, what does it mean? Oh, sorry, I should say two things. Parallel and evenly spaced. What does it mean? Can I call someone to answer? Who is YQ? Who is YQ? YQ, you want to answer? YQ don't want to answer. Inyan?
To indicate that the field strength is constant.
Field strength is constant. Some more, one more thing. Constant, you mean in terms of magnitude lah?
Yeah.
And
like
one more thing.
Same everywhere.
Same everywhere and same direction. Okay, thank you. Yeah, and that is really the case, right? You see, why do we use MGH? Why do we just say that the G is 9.81 like in our daily problems? Because, right, near Earth's surface, we expect, right, that the field lines to be constant. Or we expect the field strength to be constant. Why is that so? That is because, right, going by this entire zoom in exercise, right, indeed, okay, the conclusion is, right, at a in a region, right, near Earth's surface, the field lines are parallel one and evenly spaced, no preference. Therefore, everywhere is 9.81. And hence, right, ask yourself this question: where will this 9.81 thingy, right, fail? Well, then it's straightforward. You go the reverse direction. When you go far enough away, it's no longer 9.81 because the gap between the lines will not be the same anymore. Yeah, this part, right, trips many people. They always very confused. Why can't we use 9.81 when we are in outer space? Yeah, why is G not just like in the same way as near the surface, so on? Yeah. So let's go through. Let's not go through the example one. You can go and try. It's too time consuming. So try out the G at the sea level and Everest. You can have an appreciation of the magnitude, okay, of G. Very, very small. That's why, right, we don't expect G to be much different, because our experience, right, is that we don't feel that the gravitational force is like weaker, even at Mount Everest top. Yeah, and that's a ginormous height, right, based on our perception already. It's a huge height, Mount Everest, okay, and yet the G don't differ much. You can go and try this one also. This one is to clarify, right, what is the field strength of Sun. Sun is really massive, right, compared to Earth. It's like millions of times of Earth's mass. 10 to the power of 30, okay, the order of magnitude. Earth is 10 to the power of 24, so it's a million times. So why is it that we can just say that, oh, gravity at Earth's surface is due to Earth? I mean, Sun is much bigger, right? In this exercise, right, you can go and try and see that at the distance, right, from Sun to Earth surface, that distance, right, the G due to Sun is really small already compared to due to Earth. Okay, it's not small by absolute terms because, right, it is what that kept Earth and all planets, right, orbiting around the Sun. But it is small, right, compared to the influence of Earth on Earthlings. Okay. Just appreciation of numbers. This few slide I'll just skip is just feel the numbers. Okay. 5 km altitude or 9.81, 10 km altitude 9.80, space station 400 km above Earth surface, 6,800 km from center of Earth, 8.7. Yeah. At the moon, how far is pretty far already, right? Then you can start to see, right, that the G due to Earth, right, is like quite small now. Yeah. To put things into perspective quantitatively, right? So these are all the things. Recently, right, we put another telescope up in outer space, I think by NASA, the Weber telescope. Weber telescope, right, is somewhere around the same altitude and as the Hubble telescope. Yeah. Why they must put telescope in outer space, right? Because put in Earth, right, you have atmosphere, and it interfere too much, too many things on Earth's surface already. It interfere the signal, right, coming towards the telescope. So that's why you need to send the telescope to outer space, whereby there's like next to nothingness around it, nothing to interfere with the signal. So it can capture, right, the signal from outer space. What is the role of Weber telescope, the new one that they just put up? To detect, right, the presence of civilizations out there in the greater universe. Okay. Why there? Because, right, civilizations, when they reach a certain technological advancement, right, they will always try to make themselves known. Okay, they will send out signals, right, to outer space and say, hello, any one of you out there, something like that. Okay, so we are trying to pick up this signal to deduce, right, is there anyone or not? Yeah. I hope the experiment give a negative result. Okay, I really hope so. If you can detect something from anywhere, right, whoever sent out that signal, got to be damn powerful, such that the signal is receivable at such great distances, right, when we are at Earth, because we confirm cannot send out a signal that other people can receive. And if other people can send out a signal that we can receive, right, means that their technology is a lot more powerful than ours. And if, right, they know where we are, we are gone already. So let's keep quiet and be quiet in the universe. Yeah. Anyway, just now this curve, right, is also to show you the shape of the 1 over r squared. I want you to pay attention to this part here, okay? On where my cursor is pointing. This part, right, it is cutting this Earth's radius, right, at a fixed value. It is not asymptotic upwards. This part is not asymptotic. You may be tempted to think it's an asymptote because of 1 over r squared. Yeah, your math tells you that. But no, here is a finite value, which is 6.4 times 10 to the power 6 meters. But what is happening, right, under Earth? This part is not in syllabus, okay? I will just tell you, right, very briefly what's happening, that some of you may be interested. Is, right, suppose you have Earth and you want to figure out a point P, right, which is inside the Earth. Point P, right, has the green region above it in the radial sense, have the yellow region beneath it, okay, in the radial sense. So the simple conclusion, right, is that the green region will have no effect on the gravitational field strength at point P. So leaving only the yellow region. So we skip the yellow-green part, focus on the yellow part. So what is the G due to this portion of the mass? So we know that G is equal to Gm over r squared. But yet, right, the m is not the original mass because we clip away the outer layer, or leaving only the yellow part. So you need to ask, right, this mass is how much? Going back one step, mass is density times volume. So you have this manipulation, or rho times 4 pi r cubed. Summarize it, you end up, right, have something like this: 4 pi g times rho over 3. These are all constant. Okay, if you assume Earth to be uniform material, so uniform density, in that case, right, under the Earth's surface, the G, right, will simply be proportional to R, because you only see G is equals to one huge chunk of constant times R. Okay, so the graph will just be a straight line. Never will come up in exam. Okay. I'd like to make a disclaimer. Unless you're in RI, or RI questions sometimes may be very tricky, okay, set in this kind of ways. They will provide you with enough clues to do it, but you have this kind of thing coming out, which is challenging. Okay. Okay, so let's consider a scenario, right? Suppose we have the same Earth, but due to some strange things happening, right? This is purely thought experiment. Earth starts to collapse and shrink, or shrink into a smaller size. Let's say half the radius. What will happen? Well, you see, right? Now currently, right, Earth's surface is 9.81. If shrink to half the radius, or shrink to much smaller, right? Or not just half, shrink to much smaller, with the same mass, right? Then you'll see, right, you extrapolate this 1 over r squared graph inwards. Now you can extrapolate, because, right, we are talking about Earth becoming smaller. We are not talking about going inside Earth. Yeah. So you extrapolate the 1 over r squared graph, right? And then you realize that as r decreases, right, 1 over r squared will increase dramatically. Yeah. It's not proportionally, it's dramatically, because, right, you start to get closer and closer to the mathematical function, or the mathematical behavior of an asymptote. So if you make the r really, really small, so this is still the same Earth, nothing changed, except it shrink and shrink and shrink until really small. What will happen to the surface, the G at the surface? Well, you will approach a scenario, right, whereby it's pretty scary, which is what black hole is about. Huh? People always say, right, black hole is like some huge black color thingy, right? But actually, right, what is the nature of things, right, of a black hole is that black hole is actually something called a singularity. It's actually a point. But, right, its gravity, right, is so small. Its radius, right, so small, but its mass, right, is large, such that the G is very, very big. Okay, the G is very, very big. The black color portion, right, is not the size of the black hole. The black color portion, right, is something what we call the event horizon. Our syllabus, by the way, this is just for fun. What's happening at the event horizon, right, is that light can't even escape already. Or there's something called escape velocity, which we'll cover later on. If light can't even escape, right, you see darkness, because nothing comes out from there, not even light. So if you see darkness, right, then at points near the black hole, right, then you need to ask, at which point, right, will it be such that, right, the G is small enough for light to escape? Well, you'll be right at the event horizon. So while black hole is very small, but the region of space around it, right, where light cannot escape, right, is pretty. Yeah, and that's what we see from one movie I recommend strongly. Okay, now since it's still the last few days of holiday, right? If you have not watched it, right, please watch the movie called Interstellar. Okay, it's not a blockbuster that will make you sit on the edge of your chair, but it's a classic, super good. It's made in 2015 or 2014. I forgot which year. I watched like 5, 6 times or 7, 8 times. Very good. As I say it to you, I feel like watching it tonight again. Okay, so why like that? Why the person will get spaghetti fight, right? This one I don't want to say already. This is due to something called the effect, right, whereby something get closer to a region with very, very large G, right? The length, the dimension of something will be stretched until very long. So if a human, right, get near a black hole, you will be stretched because, right, your you see, if you like drop into a black hole vertically, right, your feet, the G at where your feet is and the G at where your head is very different. So your feet, right, will actually accelerate much faster than your head. So what will happen to you? You get put, right, by a much bigger force at your feet compared to at your head. And you will end up, right, get pulled into a spaghetti. Because someone is like pulling you stronger at the feet than at your head. So that's what it meant, right, in a simple layman way. And that's what it meant by here. So if you see your the distance r is very small until, right, your head and your tail, right, are at different r, and that will also mean, right, your head and the tail will have very different g. Okay, but not in exam. Let's skip. Okay. This chart, right, tells us the actual value of G at different parts of Earth's surface. How do people do this experiment? I'm not too sure, but there will be a way, right, that people can measure G. Okay, except we are not too sure, but that's how it looks. What we need to understand from here, right, is what is the effect? Okay, and you can see, right, the color scale, right, tells you where is the G strong, where is the G weak. When you have, right, the more red region, that will be where the G is higher. Okay, yeah, on the Earth's surface. And you can actually see some pattern because you see where mountains are, the G seems to be a bit stronger. So it's not just, right, by calculation, there seems to be something different. Okay, some factors that may really affect this G, right, we'll go through them because this is part of exam. Okay, number one, Earth, right, is not a perfect sphere. That means, right, although you apply the GM over R squared formula at different part of Earth, but you got to realize, right, that R is not constant. Okay, everything kept constant, right? Let's say the density is constant, all the material on the Earth's surface are the same. Okay, which we know is not, but we are just hypothetically keeping them constant. Then, right, even so, R is still not the same. Okay, fatter at the equator, smaller at the poles. Next thing is the density is not the same. When you are on the ocean, yeah, so they will cause the G at the surface to be slightly different because of different material. If you are standing on top of a piece of ground underneath, right, there's a huge oil deposit. A lot of dinosaurs used to die there. They rot and give rise to a lot of oil. There's an oil field underground. Oil is less dense, right, than rocks. Yeah, so people use, right, variation in G to figure out what's underneath. And for oil exploration, that is one of the method. Yeah, they take a gravitational field meter, walk around. Oh, here the value T is smaller than usual. Or we suspect underneath may have oil. Yeah, something like that. Next, this part is in exam as well, and very, very difficult for students to appreciate, which is, right, Earth is rotating. So you know from circular motion, right, that Earth's rotation, when you are you're on Earth, you are following Earth's rotation. So consider you as an object, right? Let's go to the next slide. Let's look at the North Pole guy. The North Pole guy, right, don't rotate. I mean, he do rotate, but his rotation, right, the radius is 0. He's just doing ballet at the pole, or just rotating about the same spot. If you view from a point outer space, like what we are viewing now. So his radius, right, is essentially 0. Because it's not performing a circular motion about anywhere. It's performing a circular motion about the center of himself. Yeah. Whereas, right, the guy that's at the equator, right, is like swinging a big circle. Yeah. And we know by now, right, if there is circular motion, something must provide for the centripetal force. Yeah. In this case, right, there must be a net force on the man who is on the equator. Okay, so the man standing at the equator, right, net force is non-zero. It's actually towards the Earth's center. And with that, right, we can solve problem. I think this one we can look at the greater detail. Okay. So for this problem, right, we are talking about the measurement on the scale, right, for an object on equator. So we draw out the free body diagram of the object. We must realize, right, net force must be towards the center of this circular motion. So net force must be non-zero. So mg must be bigger than n. Okay, so the red arrow longer than the blue arrow. Something that is important to note right away. Hence, right, you use F equal to ma to solve. So Fg minus n equals ma. So what's n? N is equals to Fg minus mac, centripetal acceleration. Now, right, how do we know how large is the centripetal acceleration? We could use what we know about this circular motion, because on Earth's radius, right, on Earth's equator, when we are spinning, right, we're spinning together with Earth. Earth's period is 24 hours. So you substitute these things in. So the apparent G, right, you see the first line, right, why do we start to jump into this apparent G? Because, right, you take n divided by mass. So all three terms here, right, you divide by mass. N divided by mass give you the apparent G. Okay. And the other two terms, right, Fg divided by mass give you just G alone. Then ma divided by mass give you A alone, which is R omega square. So you do this calculation, you realize, right, it's a fixed value, or is 9.80. And it's regardless of what you are considering. Yeah. It doesn't matter whether it's an elephant or a crate or a mouse. The apparent weight, apparent G, right, at Earth surface on equator will be just this value. So this calculation, right, you must know how to perform it. Okay.